Now, we get to think about this in time-dependent manner. When it's time-dependent, we call it dynamic. Using this equation, you can guess how the amount of active TLR will change on the given amount of LPS. When there's no LPS, that is LPS is 0, then this reaction will not happen because moving to the active TLR compartment requires LPS, and there's no LPS, there's no transition, so nothing happens. So without LPS, active TLR will stay 0. Now, suppose that LPS is added, but LPS amount is exactly KD. And what does it mean? It means that, as you have discussed previously, the active TLR infinity will be exactly half of TLR. This line indicates total TLR. So no matter how much LPS we have, it will stop short at exactly 1/2 of TLR. So over time, when the time is long enough, it will reach this level, which is 1/2 TLR. Of course, if time is not enough, then it will start to decay again. When the LPS is given for an even shorter amount of time, it will not even reach the steady state, and then decay halfway. When LPS is given in a really extremely short time, then active TLR will not really increase because there's not much time for active TLR to form. Now, if LPS is much higher than KD, it will reach the total amount of TLR given enough time. But then, because it now has a long stretch to travel, initially there will be a longer span where it acts like the increase is linear. So all those things tell you why we can suppose that LPS is roughly, the concentration of LPS will be roughly proportional to the concentration of activated TLR. But you should note that this does not work if there is inactivation or internalization of TLR. If we have internalization, the equation will be written in a different manner. So now we had up to now LPS plus inactivated TLR makes activated TLR with forward rate but then there's a spontaneous dissociation. This is the equation so far. But then when it moves back, this inactivated TLR is still available to bind with LPS. The interaction we have talked about is simply between LPS binding to TLR, and sometimes it dissociates. But when we talk about inactivation and internalization, the TLR receptor itself comes into the cell, so it is now available to the outside LPS. When this happens, this is just like quarantine. activated TLR will be internalized. And will become available back again long time later. Then this dynamics can be described. But because of this quarantine compartment, even when LPS is available, the subsequent reaction can be stopped, simply because TLR can listen to the LPS. In that case, inflammation can be stopped spontaneously. But in fact, such does not happen. So when LPS is available, the reaction can be ongoing and inflammation can become worse. The reason why biology is made this way is because we cannot stop listening when there's a harmful molecule out there. But in the case of neurons, if there's a barrage of glutamate receptor can internalize and stop listening. It's like when one person is saying and repeating the same thing again and again, you do not have to listen. So you internalize your glutamate receptor and stop listening. And this is the process that actually happens in neurons, which we might consider in future lessons. So next, we'll move over to the intracellular signaling kinetics. The LPS to TLR pathway is over. Now after activation of TLR, we'll study how the I kappa B and F kappa B complex can dissociate. And all those processes can be described in a similar principles. Thank you.